Good morning, everyone. Good morning. Hope all is well. Everybody's doing all right. Hope you had a great weekend. Everybody's ready to get going on this Monday morning. I know I'm dragging a little bit, but hopefully you guys aren't. Let's see. Okay. So I believe this is where we are today. The section is (17.3).
Hey, Mr. Tucker.
Mm-hmm.
I just wanted to let you know that I'm going to be kind of listening, but I'm also going to be in and out because my bathroom flooded last night and it leaked through my ceiling into my kitchen.
Oh, wow.
So yeah, so my entire kitchen was flooded last night around like midnight. So I'm going to wait for maintenance to come because they're going to be in and out. So.
Gotcha. Miss Lane, you having a lot of stuff going on.
Man, 6 months pregnant, my house is falling apart, man. This sucks.
Sometimes you gotta laugh at it though. Sometimes you gotta laugh at it.
I'll catch up, I promise, I swear.
It's all good. It's all good. I understand.
Thank you, sir.
Not a problem. All right. So looking at 17.3 for us. Simplifying radical expressions. So we talked about before, whenever we have this type of scenario, the cube root of a to the 12th. That's the same thing as raising a power to another power. And so that cube root is the 1/3 power. So you have a to the 12th raised to the 1/3 power. Whenever you have a power raised to another power, that's multiplying your exponents. So that will give us 12/3. And then you would simplify that 12/3, 12 divided by 3 as 4. So in other words, you would divide this 3 into the 12. You know, that's a short way of doing it or looking at it, but that's the process. You know, you're taking that 3, the index of your radical, dividing it into the power of your exponent. But what if the number or the power of my exponent isn't divisible by the index of the radical? All right, so of course, 17 is not evenly divisible by 3. So you see what I have here in the red, we're going to find the largest number divisible by the index of the radical. I'll put a shift set to find the largest number. Probably could have worded that a little better, but we want to find the largest number less than 17. Probably should put that right here. Find the largest number less than 17 that's divisible by the index of that radical. All right. So this is what I mean. So notice I broke it up into 15 and 2. 15 is the largest number that's divisible by 3, but less than 17. All right. So I break this up into 15 and 2. 15 plus 2 is still 17. But I can take the cube root of a to the 15th, which would be a to the 5th, because 3 divided into 15 leaves you with 5. And then a squared, I just leave that under the cube root. Can't do anything with it. So basically you break it up into what you can take the cube root of and what you cannot take the cube root of. This is what I can take the cube root of. This is what I cannot take the cube root of. Break it up that way. Then I simplify this piece and leave the other piece the same. All right. Any questions on that before we do another one? Make sure we're okay. So looking at this one right here, we have the square root of p to the 5th, q to the 9th. So here in the red, I was giving you a reminder. Don't forget, if you don't see anything, they assume you know that there's a 2 there. Any other number, there will be a number there. So if it's cube root, 4th root, 5th root, 100th root, there will be a number there. The only time that you see nothing, they assume you know there's a 2 there. So 2 does not divide into 5 or 9 evenly. So I need to break those numbers up into the highest number under 5 that's divisible by 2, highest number under 9 that's divisible by 2. And so that's what I did here. 4 plus 1 is still 5, but I know I can divide 2 into 4. And here, 8 plus 1 is still 9, but I can divide 2 into the 8. So then I break it up into what I can take the square root of and what I cannot take the square root of. So then you go ahead and divide the 2, because of square root, into each one of these exponents. So 4 divided by 2 is 2. 8 divided by 2 is 4. So that's why we have p squared, q to the 4th. And then I leave these under the radical. All right, any problems? All right. This one, doing the same thing. We have the 4th root of x to the 15th, y to the 28th. You want to be able to divide 4 into each exponent. So you want to be able to divide 4 into each exponent. So 4 divides into 28, that's over the y, so that's fine, but it does not divide into 15 evenly, so we want to break it up into the largest number under 15 that 4 can divide into evenly. So that's why we break up x to the 15th into 12 and 3, because it can divide into 12, but then we have 3 left from that 15. 12 plus 3 is still 15. Once again, y to the 28th is fine because 4 can divide into 28 evenly. Then you break it up into what you can take the square root of, what you cannot take the square root of. I mean, not square root, or 4th root. We're dealing with the 4th root. This should stay the same as far as your answer is concerned. And then you go ahead and divide 4 into each one of these exponents. And that's how you get x cubed, y to the 7th. Any problems? All right, can I scroll up? Everybody okay? All right, so with these, I was reminding you of the process that we take on when it comes to just regular numbers. Same thought process and breaking it up into what you can take the square root of, what you cannot take the square root of. When you look at the square root of 18, you know that you cannot take the square root of 18 evenly, but you break it up into factors in which one of your factors you can take the square root of. So here, we wouldn't use 6 times 3 because I cannot take the square root of 6 or 3 evenly. So I break it up to 9 times 2. take the square root of 9, which is 3, and then I leave the 2 under the radical. So that's how I have 3 square root of 2. Same thing with the square root of 500. I'll break that up into 5 times 100, take the square root of 100, which is 10, and I leave the 5 under the radical. All right. Then in the same fashion, if I have the cube root, so always make sure you pay attention to the index of the radical. If I have the cube root of 250, I need a perfect cube as one of my numbers, one of my factors of 250. So I break it up into 125 times 2. Take the cube root of 125, which is 5, and the cube root of 2 stays the same. So always make sure you pay attention to the index of your radical. All right, any problems with that? All right, so if we have a number in front of your variable and your exponent, so you have to consider both of those type of thought processes. And we're looking at a cube root. So 81 is not a perfect cube. So we need to break it up into factors that give us a perfect cube. So I did 27 and 3. 27 times 3 gives me 81, but 27 is a perfect cube. So once again, notice my setup. I'm breaking it up into what I can take the cube root of, what I cannot take the cube root of. You know, that's always what's left over. And then looking at this y to the 17th. Now 17 has to be divisible by this 3 in order for me to be able to take the cube root of it evenly for an exponent. So we know 17 is not divisible by 3, but the highest number under 17 that's divisible by 3 is 15. So I break that up into 15 and 2. So it's 15 plus 2 gives me the 17 back. So notice the difference in how we look at numbers in front of your variable, which are your coefficients, versus numbers that are your exponents. So now we take the cube root of this. Cube root of 27 is 3. And then y to the 15th, cube root of y to the 15th is y to the 5th. And then we leave the 3 y squared under the radical. Any questions? All right. Doing it again, just adding a little more to it. This time we have the fourth root of 48, p to the 9th, q to the 10th, and r to the 4th. So looking at the fourth root of 48, can I take the fourth root of 48 evenly? So I break it up into 16 times 3. I can take the fourth root of 16, and I leave my 3 under the piece that I cannot take the fourth root of. Then I'm looking at 9, 10, and 4 as my exponents. And you want to evaluate, can you take the fourth root of either one of them? So you cannot take the fourth root of 9 because 4 doesn't divide into 9. So you break it up into 8 and 1 for your exponents, 8 plus 1. Because you can divide 4 into 8. Same thing with 10. Break that up into 8 and 2 though, because you can divide 4 into 8, but not the 10, and it leaves you 2 over here as a remainder. And then r to the 4th is fine because 4 divides into 4. So that whole thing is under this radical. And here's the result. 4th root of 16 is 2. And then divide 4 into each one of your exponents. Leaves you with, hold on. Sorry, I had a sneeze. And then when I tried to hit mute first and tried to hold my sneeze went back up. Just didn't want to sneeze in you guys' ear like that. But all right, it's gone now. So 4 into the 8 gives you a 2, and then 4, dividing to it evenly just leaves you R for your exponent. So that's 2p squared q squared and R, and then here 4th root of 3p squared. All right, any questions before we get to the next one? All right, so here, let me erase this. This is the original problem. We have the cube root of 16, x cubed, y to the 9th, y to the 12th, over 2 x cubed, wait, hold on, I said that, let me say it this way. The cube root of 16, x cubed, y to the 9th, over 2 x cubed, y to the 12th. I think I said it a little funky at first, but. All right, so with this one, what you want to do is to simplify first before you look at trying to apply the cube root. So first thing I would do is cancel out x to the cube, x cubed over x cubed. And then we recognize that we have y to the 9th over y to the 12th. Whenever dividing your exponents, you're going to subtract, or dividing your variables, you're going to subtract your exponents. Then also the easiest one, I skipped right over it, 16 divided by 2 is 12. I said 12. 16 divided by 2 is 8. All right. So that gives us this setup right here. Still haven't done anything with this cube yet, but we have 8. 16 divided by 2 give you the 8. And then 9 minus 12 will give you -3. All right. So now that we've simplified everything under the radical, we can look at applying the cube root. So the cube root of 8 is 2, because 2 times 2 times 2 give you 8. Then apply the cube root to that y to the -3rd. All you're doing is divide. Just reminding you, dividing that 3 into -3, that gives you -1. And then to write it as a positive exponent, you drop that y to the -1st power down to your denominator. So it gives you 2 over y. Any problems? All right, let's do another one. All right, so here we have 4 square root of 48 over 24. So now this 24 cannot affect that square root of 48 because the 48 is under the radical, the 24 isn't. So you can't, those can't affect each other because one is under the radical, the other one isn't. But what can simplify is the 4 and this 24 that's sitting on the outside of the radical. So 4, there's a 4 that divides into both of them. So there's a 4 that's in each one of them that can reduce. So that'll simplify to the square root of 48 over 6. Now I'm looking at breaking up this 48 into 16 times 3 because I need to be able to take the square root of whatever I break up the 48 into. Square root of 16 is 4. Leave the 3 under the radical. And that would leave me with 4 square root of 3 over 6. And once again, we can reduce. So that's a 2. That's in common with the 4 and the 6. Cancel out that 2. That'll leave you with 2 over 3. And that'll be your answer. 2 square root of 3 over 3. One second, checking something out. Distance formula, midpoint. All right, we'll go here next. All right, let me check out one thing in your homework. Saw that had distance formulas in it. Okay. All right, so let me go to here. I just thought about something that there's something in the section that the other book didn't have. So we can do this to make sure you guys are straight. So it's still 17.3. Let's go over some of these rules real quick just to make sure you guys don't see anything that not gonna do all of these notes out of 17. I mean, it's just like I said, just extra stuff. I want to make sure you guys see some things, certain things like this we have to do, and this. Okay, not much, but a few more things extra. All right, so this is still 17.3, but I forgot that this section in the other book, well, this section has a few different things than the other book did. So I want to make sure you guys are straight when you go looking at it. So we talked about it already, but just putting a name on the rules, that's all. And, just reemphasize a few things, so it'll be all right. So here we have the product rule. As long as the index of your radicals are the same, you can multiply what's under the radicals. That's what this is saying. So the nth root of A times the nth root of B would be the nth root of A times B. So that's your product rule. So first example, if I have the square root of 3 times the square root of 5, that's going to be the square root of 15. I'll just multiply what's under the radical. As long as the index of your radicals are the same, you can just multiply what's under the radicals. Same thing here, cube root of 4 times the cube root of 2. It's going to be the cube root of 4 times 2, which is the cube root of 8. But then you can simplify that further because the cube root of 8 is 2. Because 2 times 2 times 2 will give you 8. All right. And then here, 4th root of 5y squared times the 4th root of 2x cubed. 5 times 2 is 10. y squared, and then x cubed. Multiply that together, gives you what's under the radical here. Cannot take the fourth root of any of that. All right, any problems with that before we look at the quotient rule? So same thing happened with the quotient rule. As long as your index or the radicals are the same, you can go ahead and divide those. Divide what's under the radical. All right. And it works the other way around. If you want to break it up, let's say if you had this and you want to break it up like that, you can do that as well. So both of these work the same way. So if I have the square root of 25 over the square root of 49, I can break that up to the square root of 25 over the square root of 49 separately and just take those square roots. Square root of 25 is 5, square root of 49 is 7. All right. So here in B, I have the square root of x over 9. Take the square root of each one of those individually. Square root of x, nothing I can do with that. So you just leave it, but then the square root of 9 is 3. All right, any problems? So the same thing happens with the fourth root. So any index, any radical, you can do the same way, use the same process. So we have the fourth root of 3 over 16 y to the fourth. Break it up into the fourth root of 3 over the fourth root of 16 y to the fourth. Fourth root of 16 y to the fourth is just 2y. Any problems? And so we did that already. D, it is possible for something that cannot, they may give you one that cannot be simplified. If you look at the factors of 16, remember we already talked about breaking up numbers. We did that. Well, remember we had the square root of 500 in the other notes. So we already did this, but just in case they give you one, it is possible for them to give you something like the square root of 26, cannot be simplified or something of that nature. So just make sure you're careful. Don't make up stuff mathematically, We already did that. That was the first thing we did in the notes. So not shortchanging you, but I just want to make sure that we have names on what we did. We already did that. Yeah. So here is the other thing that's in this section. We're looking at the distance formula. All right. So that's D equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And x2, x1 comes from points on your plane. So whichever one's point 1 is x1, y1, coordinates of x1, y1, whichever point you call a point 2 is the coordinates of x2, y2. So you're just talking about the distance between those 2 points. All right. So direction would be find the distance between 2, -5, and 1, -4. It's always good to label which one you're calling point 1, which one you're calling point 2.
So I just called the first one I see 0.1, second one 0.2. Doesn't matter which one you call which. All right. Plug them in the formula accordingly. X2, which is 1 minus 2, which is x1 squared. Y2 minus y1, -4 minus -5. Make sure you don't lose negatives when you do your substitution. End up being -1 squared plus 1 squared. Of course, 1 squared is just going to give you 1. 1 plus 1 is 2. So this is square root of 2. So it depends on what they ask of you. If they ask for the exact, this one is your exact answer. But then once you apply the square root to the 2, that's going to give you a run-on decimal. This is your approximation. So if they ask for the approximation, they'll tell you how many decimal places around that all to as well. So they could ask for either one. All right, any problems? We're looking at the midpoint formula. All right, so here's the midpoint formula. Talking about the coordinates of the point that's in the middle of 2 points. So it's x1 plus x2 over 2, y1 plus y2 over 2. All right, so tell us to find the midpoint of -3, 3, and 1, 0. Once again, I decided to label the first point that I see 0.1, second one 0.2. Plug the values in according to your formula. x1 plus x2, -3 plus 1 over 2. y1 plus y2, 3 plus 0 over 2. And there you go, -2 over 2, 3 over 2, -2 over 2 simplifies to -1. And you can leave the 3 over 2 as a fraction. If you divide into a decimal, that would have been what, 1.5. All right, any questions, any problems? Very good. Before I go to the other page. All right. Probably want to leave myself a note. All right. So let's look at 17.4. So we want to add and subtract. Let me see, did they make multiplication a separate section? No, all of it's the same. Okay. Rationalize denominators. Okay, so add, subtract, multiply, radical expressions. So in the red, you see the conditions that we need in order to add and subtract. Our radical expressions need the same index for your radical and the same radicand. So we're just talking about adding. You know, we talked about multiplying a little bit already when you didn't need the same radicand because you can multiply what's under the radical. But here we're talking about adding and subtracting. So you need like terms. You can think about like terms, like, you know, common terms. So you need the same index for your radical. Here's square root 2. And then you need the same thing under the radical, which is your radicand. And that's why. If you don't have the same index for your radical and you don't have the same radicand, in other words, what's under the radical, you cannot add these expressions. So we have 6 square root of y plus 4 square root of y, and that's 10 square root of y. All right. So here's just an example of when you cannot do it. Notice we have the square root of y. Here we have the cube root of y. So you cannot add them together. If your indexes are different, you cannot add them together. Erase this. Here we have 6 square root of y plus 4 square root of y. So this time we have the same square root, but what's under the radical is not the same. So you cannot add them together. So before it was your index that prevented you from doing so. Now in this one, it's what's under the radical, your radicand that prevents you from doing so. All right, any questions? All right. So here we have 9 square root of 3 minus 6 square root of 3 plus 5 square root of 5. So all of these have the square root, but 2 of them have square root of 3 and the other one has a square root of 5. So all you can do is combine what you can combine, and the other part you leave as is. So that's what we did here. 9 minus 6 gives you 3, square root of 3. And then this square root of 5, you just leave right here. So this is your most simplified expression. Over here in the purple, I guess someone asked me a question. I have 3, 4th root of 7, plus 8, 4th root of 7. All of this is the same, 4th root of 7, so you can just add what's in front of it, which is 8 and 3, and that gives you 11, 4th root of 7. So just another example of being able to add like expressions. All right, any questions if I scroll up? All right, so this next one, we cannot simplify it. We have 5 square root, or the 5th root of 5b plus the square root of 5b. So one is the 5th root, one is the square root. So we cannot do it. All right, so there was nothing that we can do with the 5b under those radicals. But you should explore that. So when we look at what we have here, 4 square root of 28 plus 3 square root of 175. You do want to analyze if it's possible to simplify what's under the radical, or simplify this radical expression to see if you can add the terms in their most simplest form. So you don't want to just look at it and be like, I can't do nothing with it. Now, if your indexes aren't the same, then there's nothing you can do. You can't change the index of your radical. But what you can do is look and see if you can break down square root of 28 and square root of 175, since we both have the square root, since both of them have the square root involved. So that's why I wrote right here, simplify as much as possible. Once again, if one had square root and the other one had cube root, then there's nothing you can do with that. So they may just ask you to write simplest in lowest terms. Then you can still break it down, but you wouldn't be able to add them together because one has cube root, one has square root. But since both of these have square root, we can break these down. Square root of 28, I can break that up into 4 times 7, taking the square root of 4 and leaving the 7 under my radical. So that's 2 square root of 7. 175, I can break that up into 25 times 7, taking the square root of 25, which is 5, and leaving 7 under that radical. All right, so before we go any further, make sure we're okay. All right. So don't forget we did have a 4 and a 3. That was a part of our original equation, so we can't leave that alone or forget it. So square root of 28 is right here. Square root of 175 is right here. But you have 4 times the square root of 28, 4 times, and 3 times the square root of 175. So that's still represented in this whole expression. But then we have 4 times 2, which will give me 8. 3 times 5 will give me 15. So this is our most simplified way of expressing what we had originally. And now we see that we can add those together. 8 plus 15 gives me 23 square root of 7. All right. Any problems? All right. So let's do it again. This time we have the square root. Well, not square root. We have 7 square root of 8 minus 3 square root of 27 plus 2 square root of 72. So that's the breakdown of all 3. We have square root in all 3. So it's possible that we may be able to add and subtract them accordingly, but we have to break them down to see if they will allow us to do so. So looking at 8, that's square root of 4 times 2. Taking the square root of 4 leaves you with 2 square root of 2. 27, you break that up into 9 times 3. Taking the square root of 9 leaves you 3 square root of 3. And then 72, break it up into 36 times 2. Taking the square root of 36, that'll leave you with 6 square root of 2. All right. Any problems with the breakdown? All right. So now let's analyze what we have. Put those 3 pieces back into the problem. So that's 7 times 2 square root of 2 minus 3 times 3 square root of 3 plus 2 times 6 square root of 2. So remember, we had that 7, 3, and 2 in our original problem here, so we can't lose them. So 7 times 2 is 14, 3 times 3 is 9, 2 times 6 is 12. But we cannot combine all 3 of these because one of them has the square root of 3, while the other ones have the square root of 2. So you just combine the ones that have square root of 2 and bring down the one that has the square root of 3, just like combining like terms. And this would be the most simplified way of expressing our original problem. Any problems? All right. Have any more? Okay, got another one down here. Let me see how many more we have. Okay, never get to multiplication. All right. So we have a square root of 45 minus 5 square root of 125 a squared. Once again, same thought process. We're going to break this stuff down as much as possible to see if we can subtract these expressions or these terms. So square root of 45, we break up into 9 times 5. Take the square root of 9, which is 3, leave the 5 under the radical. Square root of 125, we can break that up into 25a squared and 5. So I can take the square root of 25a squared. So don't forget that variable back there. You can take the square root of a squared and leave the 5 under the radical. And that's 5a square root of 5. All right, is everybody okay? All right, so here is plugging it back into our original expression. Don't forget, once again, we had these numbers that were sitting outside of our breakdown, so don't lose them. So that's a times 3 square root of 5, 5 times 5a square root of 5. Multiply that. It gives us this. 3a square root of 5 minus 25a square root of 5. So notice over here in red, these three things had to occur because now a variable is involved. We have to have the same index, same radical, and same variable. You know, if this a wasn't here, or if you had a squared and one had a, you wouldn't be able to add them or subtract them. So whenever you involve variables, now you have to consider like terms like you would any other time. So all three of these things occur. Same index on your radical, same radicand, you know, what's under the radical, and same variable. All right, any problems before we look into multiplying? All right, so I don't know if I said it, but 3a minus 25a is negative 22a square root of 5. Yeah. All right, so multiplying. If I have 3 square root of 5 times 7 square root of 2, you multiply the numbers on the outside of the radical, multiply the numbers under the radical. Like I said, we kind of did this already in the first part of the notes of the last section. The breakdown of this, you know, it's a little different. So, you know, nothing wrong with rehashing it, making sure we're good with it. So 3 times 7 give you 21. Square root of 5 times square root of 2 is square root of 10. 5 times 2. Any problems? Yep, scroll up, see the whole thing. Was everybody done with that first one? All right. So here, this next one. square root of 12 times square root of 28. It's easier to break it down first before you multiply. Now I can multiply the square root of 12 times the square root of 28. I'm going to get a larger number, maybe an unfamiliar number, which would make it harder for me on my breakdown because the number is unfamiliar. So it's easier to break it down while the numbers are smaller and the numbers are more familiar to me, then multiply these numbers together. So that's what I did here. I broke down the 12 into 4 times 3 to the square root of 4, which is 2. That's the 3 under the radical. Then same thing with 28. That would end up being 4 times 7. Take the square root of 4, which is 2, leave the 7 under the radical. So now I have this as my multiplication process versus 12 times 28, and then trying to figure out how to break that up. So it's all about dealing with numbers that are smaller and more familiar to us, if possible, right? So now multiplying this together, 2 times 2 is 4, 3 times 7 is 21 under the radical. All right, any questions before I scroll up? All right, we already did this. We can talk about it again, no big deal. All right, so here we have the cube root of a squared, b squared. Okay, we didn't multiply with it, but it's the same thought process. Cube root of 54, a to the 4th, b squared. So we multiply. Since we just have variables, go ahead and combine those variables together. So a squared, a to the 4th. If you add those exponents, that'll give you a to the 6th. And then b squared gives you b to the 4th. So that's what we did here to get right here. I probably could have went the other way with it. Yeah, I know that's too much. I'm just playing. Give you guys a chance to copy. All right, so got a to the 6th, b to the 4th, and 54 under this radical. So now I'm looking at breaking it down into what I can take this cube root of, what I cannot take the cube root of. So looking at 54, I break that up into 27 times 2 because I can take the cube root of 27. Now, can 3 divide into 6? The answer is yes. So I can use the whole a to the 6. Then can 3 divide into 4? The answer is no. So you break up the 4 into the highest divisible number under 4, but divisible by 3. Highest divisible number by 3. Oh, highest divisible number highest number that's divisible by 3 under 4. All right, and that ended up being 3. And then 3 plus 1 is 4. So that's why you have that there. So it's the same thought process we did in the last section. That's my eraser not working. All right. All right, so let me erase this. And so now we can take the, got my eraser still on. So now we can take the cube root of this. So cube root 27 is 3. Divide 3 into these exponents. That'll be 2 and 1. Leave your 2b under the radical. Any questions on that one? All right. How many more we have? Hold on, that's got to be another section. I'll check to make sure we get there. Okay, so here we have the cube root of 3. Cube is the cube root of 3 times 3 cube root of 3 minus 4. All right, so we're going to distribute just like we would if it wasn't a cube root. If it was just 3, you would distribute 3. So cube root of 3 times cube root of 3 is cube root of 9. And that 3 stays on the outside. And then 4 times cube root of 3 is just 4 cube root of 3. Cube root of 9 is 3. So that'll be 3 times 3, which is 9. And there's nothing you could do with this, just 4 cube root of 3. All right. Here we have our binomial distribution. I'm going to erase this. So we have 9 square root of 2 minus 3 square root of 3. I said 3 square root of 3. 9 square root of 2 minus square root of 3 times square root of 2 minus 5 square root of 3. And so we will distribute accordingly. So you distribute the 9 square root of 2 into the other parentheses, distribute this negative square root of 3 into the other parentheses. That leaves us with this result. So 9 square root of 2 times square root of 2. The 9 stays the same, but then you do square root of 2 times square root of 2, which is square root of 4. Then we're looking at 9 square root of 2 times 5 square root of 3. So 9 times 5 is 45. Square root of 2 times square root of 3 is square root of 6. Then we have square root of 3 times square root of 2, which is just square root of 6. Or negative, square root of 6, because we have this minus sign right here. And then negative square root of 3 times 5 square root of negative 5 square root of 3. So those negatives and negatives turns positive. Square root of 3 times square root of 3 is square root of 9. That's how we get those terms. All right, so square root of 4 is 2. So that's what I did right here. Now here, I wrote a 1 there just to emphasize the fact that when you don't see anything, assume you know there's a 1 there. So we have negative 45 square root of 6, negative 1 square root of 6. So negative 45, negative 1 is negative 46. So we can add those together because they both have square root of 6. So I didn't mention those out. We didn't mention that. And then here, square root of 9 is 3. 9 times 2 is 18. 5 times 3 is 15. I could have left that. And then 18 plus 15 is 33. Minus 46 square root of 6. All right, any problems, any problems? All right, let me make sure something in your notes, trying to figure out why it shoots to that. So we're in 17.4. Yeah, so that's the end of that. Yeah, should be looking for rationalizing the denominator. Yeah, so that's not it. Okay. Okay, so what do I happen to my notes? It's completing the square. Yeah, this is not it. Oh, my notes must have got deleted. Okay. All right, let's see. Give me my call this. Let's see, how much do we have left out of this chapter? So we have rationalize denominators, radical equations, problem solving, and then complex numbers. So let's do this section, and then we'll call it a day. All right, so rationalize the denominators, numerators. Normally you don't rationalize your numerators, but if they ask you to in a section, then you should be able to do so. So we'll make sure that we're good. So when we talk about rationalizing your denominator, you're talking about, I'll write it like this. So to rationalize the denominator or the numerator means to remove the presence of the radical. And so you can't just take off. So now let's say we want to rationalize the denominator. You can't just take the radical off of 3 and then walk away from the problem because you just changed the value of the equation. So you want to be able to do it mathematically in such a way that it's still, the effects, there's no real effect to it. It's still the same problem and it still has the same value. So if the directions say rationalize the denominator, so if you want to rationalize the denominator, you want to ask yourself, so what can you multiply to 3? Because we're looking at the denominator. What can you multiply to 3 to turn it into a perfect square? And the answer is 3, right? Because 3 times 3 is 9. So the answer is 3. Because 9 is the perfect square. So when I look at the square root of 2 over the square root of 3, I will multiply. Now, you know you can't multiply this by just 3. You have to multiply it by the square root of 3. You know, in order to multiply something times something under the radical, it needs to be multiplied by that same radical. But also remember, whatever you do to the top of a fraction, to the bottom of a fraction, you actually have to do to the top as well in order to keep your equivalency. So now we're looking at the square root of 6 over the square root of 9. And now you'll be able to simplify. Square root of 6, but then square root of 9 is going to be 3. And that will be rationalizing your denominator. Now the presence of a radical is no longer in your denominator. All right, any questions on that before we look at another one? So let's see, 5 cube root of 2. All right, want to rationalize the denominator? Once again, same thought process. This time though, we're dealing with cube root. So now we need to be able to take the cube root of 2 or whatever's in our denominator. But of course, 2 is not a perfect cube. So you have to ask yourself, what times 2 would turn into a perfect cube? In this case, it would be 4 because I put 2. It would be 4 because 2 times 4 will give me 8, which is a perfect cube. You know, so basically you're creating a scenario of 2 times 2 times 2. That's what you need down there in order to take the perfect cube. Just like here, we needed the scenario of 3 times 3. So we multiplied it times 1, 3, which gave me 9. Here we only have 1, 2, so we multiply it times 2 2s, which is 4, to give me 8. So we're going to multiply top and bottom by the cube root of 4. So it's going to be 5 cube root of 4 over the cube root of 8. Simplify. Cube root of 8 is 2. And that's your most simplified way of expressing that without your radical in your denominator. All right, here, square root of 17x over 19y. Still looking at rationalize the denominator. I don't see one talking about the numerator yet. If I see one, then I'll, we'll do it. But if they don't mention it, then that means they didn't emphasize it in your homework. So don't worry about it. So square root of 17 over x over the square root of 19 over y. Did I say that right? Square root is 17 over x over the square root of 19y. I said over y, over the square root of 19y. So we're going to rationalize our denominator. We're going to turn it into a perfect square. So we just multiply on top and bottom by the 19y. And when it comes to squares, square roots and perfect squares, all you do is multiply and times the same thing that's down here. So it just comes a little tricky once you increase your index of your radical. So let's see, 17 times 19. That'll be 323 xy. And then here, let's see, we don't necessarily have to multiply because we know we're gonna have this. And so 17 and 19 are perfect, with a prime numbers, not perfect squares, they're prime numbers. And then here, that's 19y. Now, if you wanted to do 19 times 19, you could. That'd be 361, but the square root of 19 times 19, square root of 19 times 19 is just 19. So that's the reason why you do, that. All right. Trying to find a good one here. Okay, let's look at this one. Once again, he wants to rationalize the denominator. We can break this up this way. Now the square root of 1 is just 1. Now we could reduce this. So, it depends on how you want to do this. You could reduce it now or reduce it later. I'm going to go ahead and reduce this now. Oh, good luck there. And break up this 80x into what I can take the square root of and what I cannot take the square root of, just like we talked about before. I believe 8 about 16. Yep. So break this up into 16 times 5x. I cannot take the square root of x. 16 times 5 is 80. So square root of 16 is 4. And leave that 5x under the radical. So this is what we're looking at now. But I still need to get rid of this square root of 5x. The 4 is okay, but the square root of 5x needs to be removed. So I'm gonna multiply top and bottom by the square root of 5x. All right, square root of 5x times 1.
Garage door.
So that gets rid of our radical in our denominator. And that'll leave us with square root of 5x. 5 times 4 is 20. And that'll be it. That'll be our simplified way of expressing that. All right, so let's see. Trying to see where else we're going with this. Okay, they give you a couple of numerators at the end, about 5 of them, but no, the focus is the denominator. So they just give you like a couple of them at the end. So we'll do that before we leave this section. $16.27. All right, so this time we have the 4th root of 16. I said, yeah, 4th root of 16 over 27. So we break it up. Now we can actually take the 4th root of 16, which is 2. Cannot take the 4th root of 27. So since we're trying to rationalize the denominator, we want to ask ourselves, what do I multiply to 27 in order to turn it to a perfect square, a perfect 4th root? So when we look at 27, that's 3 times 3 times 3. So we need one more 3 to make it a perfect 4 3s. So we take the 4th root of it. So that's another way of looking at it. So yep, that means we're going to multiply top and bottom by the 4th root of 3. So we have 2. 4th root of 3. Then on bottom, 3 times 27 is 81. So that'll be 2 4th root of 3. Then the 4th root of 81 is 3. And that would be your answer. All right. All right. Any problems before we let's see, it's 10:30. Let's go along to 11. Okay, so we still got a few more minutes. So before we go to the next thing, we're looking at conjugates. Right there. So when we talk about conjugates, what would be the best way to do it? So all you're doing is changing the middle sign. So those would be your conjugates. The reason why those are important because when we multiply them together, we have a special product, and you'll see what happens in a second. But it's another good one. 5a plus 7b conjugate would be 5a minus 7b, or the square root of 17 minus 3m square root of 17 plus 3m. So it's the same two terms, just that the middle sign is different. And notice I got an arrow going back and forth because they're conjugates of each other. Oh, this is too thick. I think anyway. Okay, there we go. So whenever you multiply conjugates, to your binomial distribution, x squared negative x plus y squared minus. So you have that scenario, middle terms will always cancel. Yeah. And that will be a result. So that will always be the case when you multiply your conjugates. So we're gonna use this to rationalize our denominators or our numerators. Our middle terms are always going to cancel whenever we multiply our conjugates. All right, so let's find a good one. All right, so here, still looking at rationalizing our denominator, we have 4 over 3 minus square root of 11. So we're going to multiply. I guess I'll write it here. Multiply by the conjugate of the denominator. That's the one we're trying to rationalize. If we were trying to rationalize the numerator, then we multiply, we would consider what's in the numerator, and that would dictate what we would do. All right, so multiply both top and bottom by 3 plus square root of 11. We had 3 minus square root of 11 originally, so we multiply top and bottom by 3 plus square root of 11. And then you go ahead and multiply. This is our numerator. So our denominator, multiply both of them accordingly. So in the numerator, we have 4 times 3 plus square root of 11. Go ahead and follow that. 4 times 3 is 12. 4 times square root of 11 is just 4 square root of 11. Then in the denominator, we have 3 minus square root of 11. 3 plus square root of 11. And we'll follow that. 3 times 3 is 9. 3 times square root of 11 is 3 square root of 11. Negative square root of 11 times 3 is 3 square root of 11. Negative 3 square root of 11. And then negative square root of 11 times positive square root of 11 is negative square root of 121. 11 times 11 is 121. So we notice 3 square root of 11 and 3 square root of 11 cancel. Remember, whenever we multiply our conjugates, that's supposed to happen. And then the square root of 121 is 11. So 9 minus 11 is negative 2. So something of that nature is supposed to occur when you're multiplying these conjugates. So now we have to finish off the problem. So this is my new numerator. This is my new denominator. So we have 12 plus 4 square root of 11 divided by negative 2. Now we take that negative 2 and apply it to each numerator. It's negative 6 minus 2 square root of 11. And that will be our most simplified way of expressing that with our denominator rationalized. All right, any problems with that? Any questions? All right, so then they could actually rationalize the numerator. Like the last 5 problems are actually to rationalize the numerator. Same thought process. It's just that it's based upon the numerator versus the denominator. So let's see, we had 17. Let's go something simple like 3. So let's say if I had the square root of 3 over 17 and I want to rationalize my numerator. So looking at the breakup, square root of 3 over square root of 17. Now everything is based on getting the radical out of my numerator. So I'm going to multiply top and bottom by the square root of 3 because I want to remove the radical out of my numerator. So that's going to be square root of 9 over 51. And then square root of 9 is 3. And then that 51, stays the same. All right. Problems with that? All right. Let's look at 7. All right, so here I have the cube root of 7 over 125. Once again, we're rationalizing the numerator I were to break this up, cube root of 7, cube root of 125, I can actually simplify the cube root of 125, that is 5. But now I want to get the radical out of my numerator. That's 1 7. If I want to turn it into a perfect cube, I need 2 more 7s, right? So I need 7 times 7 times 7 in order for that to be a perfect cube. So you're going to multiply both top and bottom by the cube root of 49, 7 times 7. Yeah, that's so. All right, so multiplying that will give us cube root of 343. Down bottom, this is going to be 5 cube root of 49. Cannot multiply those together. One is under the radical, the other one isn't. But the cube root of 343 is just going to be 7. And I have 5 cube root of 49. Try to write that a little neater. Let's see. And that will be that. All right, let's do one more. Then we'll be done for today. So minus 10 over -2. All right, so once again, rationalizing the numerator. If that's the case, then we're going to multiply top and bottom by the conjugate. You know, whenever we have two terms here, we're going to be looking at the conjugate. Of the numerator. So we just use the opposite sign. All right. Don't know if I emphasized that much before, but whenever we have two terms here, that's when we were looking to use the conjugate minus sign. Like before we had a plus sign where we are. No, it was a minus sign originally as well. Well, there's minus or plus, but if we have two terms, you know, and we're trying to rationalize that, that's where we have to use our conjugate. All right. So now once again, I'm gonna multiply my numerator separately. I'll simplify my numerator separately and then simplify my denominator. So we're looking at 2 minus square root of 10 times 2 plus square root of 10. Pull that out. 2 times 2 is 4 plus 2 square root of 10 minus 2 square root of 10 minus square root of 100. Middle expressions cancel for minus square root of 100, which is 10. And that is -6. All right, then my denominator is -7, 2 plus square root of 10. So we'll fold that out. -14 minus 7 square root of 10. All right. So our new numerator is -6. New denominator, -14 minus 7 square root of 10. And good to go. Let's see, let's get rid of this minus sign. Since I have a minus sign sitting out here, then I have one sitting out here and here. I'm going to go ahead and multiply top and bottom by -1. Just another way of it, of seeing this problem. So you may see it like this, may not. So just trying to prepare you for what they may ask of you. They may say that could be simplified further or something like that. So you multiply top and bottom by negative, since we have so many negatives involved. That'll be a +6, +14, plus 7 square root of 10. That's our final answer. All right. So any questions on what we did there? Or any questions on anything? All right. So as always, try to stuff out, see if you get stuck on anything. You can always bring those questions to class, or if you need to set up a time outside of class, feel free to let me know and we can see what we can make up or set up. Other than that, if you guys are good, I'm good. We'll pick up here next class, get into our next section, and go from there. So you guys have a great day, be safe, and I'll see you on Wednesday.
Quick question, is the last homework 17.5 for today?
For today, yes.
Okay, thank you.
Yep, not a problem.
Thank you.
No problem, thank you. Have a good one.
Yeah.
Thank you, Mr. Tucker. Have a good day, and I hope that baby has a good day too, because she sounds like she's having a wonderful time.
So y'all could hear it all? Yeah, so you could hear it.
Oh, I enjoy it. I have 9 brothers and 3 sisters. I enjoy it.
Oh man, well, I was hoping that the recording couldn't enjoy it, it didn't enjoy it. That was my concern. But all right, well, thanks for letting me know.
Have a good day, sir.
You do the same. Take care.